Polish national flag problem. Remember, decrease and conquer comes in two flavors. If you've seen my sorting class or maybe my array floaters, you would remember that either you do some work upfront to reduce a problem of size n to a problem of size n minus 1, and then you delegate the remaining subproblem to a subordinate. And when the subordinate solves that problem, you're done. The whole problem is solved because you've already done the work upfront uh, to handle the extreme element. The other approach is you don't do anything upfront. You first hand over the problem of size n minus 1 to your subordinate, and when your subordinate comes back, having solved the subproblem there, you extend the solution to that, to the solution of the overall problem, where you do work at the end. So that's the you can say that's the bottom up approach, which is what we discussed here. Another way to go about it would have been top down. So let's see what would happen if I were to approach this not in a bottom up way, but in a top down way. And I'm just going to assume that I'm given an array of size n, and I need to color this into a red region and a white region on the left and a red region on the right. So I'm going to just look at the first number. Right? It doesn't matter whether it's at the left end or the right end. It would work in either case, but let me just do it from the left end here. There are two options. Actually, yeah, there are two options for what this number is. Either it could be white or it could be red. If it's white, I know that I need the white region on the left and I need the red region on the right. So I don't have to do anything in that case. I have managed to reduce the problem to size n minus 1. Right? In that case, I did some work upfront to make sure to check what this number is, since it was already, or this color was, since it was already in the right place. I didn't do anything. I just handed over the remaining problem to a subordinate. Now, what if this number was red? If this number was red, what I could do is, I know this is not the right place for it because the white region should be on the left end, the red region should be on the right end. So what I could do is, I could send this number to the right end by swapping it with whatever is on the right end. And by doing so, I have again reduced the problem to size n minus 1. Right? Except that it's the first n minus 1 numbers that I've reduced it to instead of the last n minus 1 numbers. So I hand over the remaining problem to my subordinate. My subordinate again looks at the leftmost number of his or her subproblem. Let's say it's again red. Its value is again red. Where should it go? Should go on the right end. Now, suppose I have something that tells me that this region is already been painted. So I'm going to send this number to the next position, right? And so I have two numbers now in the red region, and let's say I have a red pointer pointing to the boundary or the leftmost red number. And by doing so, I would have swapped it with whatever number was here, it would have come here. I don't know, it could be white or red. I don't know what it is, but I know that I have reduced this problem size again to n minus 2 now. That person again hires someone under them and says, okay, you solve the problem of size n minus 2 here. Now this subordinate again looks at the leftmost number. Let's say it happens to be white. There's nothing to do because the white region is on the left. Go forward. So now we have So this blank rectangle is the subproblem that is passed down to the next subordinate. Maybe the next subordinate also sees that this leftmost number is again white. So then there's nothing to do. The blank rectangle has again shrunk in size. So an arbitrary worker in this hierarchy is going to receive a blank rectangle which is neither a pure prefix of the original problem nor a pure suffix, but a rectangle somewhere in the middle, surrounded by a white region on the left and a red region on the right. Let's say we have the boundaries of those two regions marked by a white pointer and a red pointer. The white pointer points to the rightmost white number, the red pointer points to the leftmost red number. Now, if I am asked, I am an arbitrary worker in this hierarchy, I am asked to solve this, I'm asked to paint this middle rectangle uh, in a way that, at the end, everything on the left of the overall array will be white, everything on the right will be red. What do? I just look at the leftmost number of my subproblem as a lazy manager. What is the leftmost number? White plus 1. That's my leftmost number. If it's white, I just increment the white pointer and I've shrunk the rectangle by 1. If it's red, I'm going to swap this value with whatever value lies here. So I know that this number is red, so the red region is going to extend by 1. So I move the red pointer to the left by 1, and then I do the swap. And I keep doing this until the blank rectangle in the middle has shrunk to nothing. So this can also be written, well, I can't write this as a for loop because I'm not painting the regions in a monotonic left to right order here. I'm looking at the leftmost number of my subproblem. Either it stays there, or I swap it, or I send it to the right end. So I'll need a while loop here, right? As long as, so till when should we continue here? We continue until this blank rectangle in the middle has a non-zero size. What's the size of the blank rectangle in the middle? Well, it's the red pointer minus the white pointer minus 1. Right? So basically all the numbers from white plus 1 to the red value, actually not to the red minus 1. The semantics, by the way, I'm keeping the semantics same as it was for Lumut's partitioning, that the white pointer is the rightmost white number, the red pointer this time is the leftmost red number, because this red region is growing in a right to left order. So um, when the blank rectangle in the middle shrinks to nothing, this is what will happen, right? This is the white pointer will be at the rightmost white number, the red pointer will be at the leftmost red number. That's the termination condition. Right? Until we reach that point, the two pointers are spaced apart by more than 1. So the termination condition is when red and white are right next to each other. So we keep doing this until the red and white pointers are next to each other. That is, as long as the red and the white pointer are not next to each other, that is, the gap between them is more than 1. Here the gap is exactly 1. Red minus white is equal to 1. While red minus white is more than 1, what do? We look at the leftmost number. right, which is white plus 1. If array of white plus 1, there are two possibilities. Either it's white or it's red. If it's white, you just have to extend the white region by 1. Otherwise, it's red. If it's red, what am I going to do? I'm going to move it to this spot. So I know that the red region will increase by 1, so I decrement the red pointer and decrement the red pointer and then swap that value, array of white plus 1, with whatever was at the right end. So this also will transform the array in the same way, except that it's going to do it from both ends. When we start out, the entire rectangle is blank. So the rightmost white number does not exist. And the leftmost red number also does not exist. So the white index and the red index cannot be valid indices in the array. So the white index starts out just outside, just to the left of index 0 here. The red index likewise should start out just outside the array index here. So this code is also as compact as the earlier code, where I was going in a single direction. Doing decrease and conquer in a single direction, but in a bottom-up way, where I assumed that the problem is already solved to my left. What do I do with this number that I'm staring at right now? Whereas here, the problem wasn't already solved. I was doing some work up front to solve it and to in particular handle the leftmost number that I'm looking at. Either I put it in the left partition or in the right partition. And in either case, I do that work and I reduce the size of the blank rectangle in the middle by 1. So that's my way of looking at Hoare's partitioning in terms of the problem solving strategies. Hoare, of course, was a Turing Award winner. He invented quicksort, quick select. He could have had a flash of inspiration or whatever you want to call it. But as an average human being, if I have to come up with something like that, how would I do it? I would use a decrease and conquer approach like this to derive an algorithm that goes inwards from both ends. There are white region on the left, red region on the right. So that's the code for Hoare's, something like Hoare's partitioning, right? I mean, the way it's typically described is, right, you keep moving the left pointer forward until you see a number that's not in its right place. Keep moving the right pointer leftwards until again, it sees something that is not supposed to be there, and then they will swap their values. And I mean, if you when someone describes it to you, obviously it's not hard to understand, but then it's not clear how how do you come up with it. So this is one way.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today